Alright, today we're working on Chapter 4, Section 5 and Chapter 4, Section 6, which is all about probability. So first, Chapter 4, Section 5 deals with theoretical versus experimental. And if you think back to the first activity we did, trotting into probability explained the difference between theoretical versus experimental. Theoretically, if you roll the dice, 7 should win every time. Experimentally, is that what happened? Obviously not. Different groups some of you had horse number 4 winning or horse number 11 winning. Theoretically, that should not happen. So, to calculate theoretical probability, you would take the number of favorable outcomes over the number of possible outcomes. Where experimental probability, since you're actually doing the experiment, you would take the number of times that the event actually occurred over the number of times that the experiment is done. So let's take a look at some of these problems. First, theoretical probability. A bowl contains 12 slips of paper, each with a different name of a month. Find the theoretical probability that a slip selected at random has a name of a month that starts with the letter J. So first of all, our number of favorable outcomes we've got to calculate. That would be the months that start with J. So that's January, June, and July. So that's 3 months. Out of how many possible outcomes? Well, how many slips of paper are in the bowl? 12. So that's our number of possible outcomes. Never leave that as your final answer because it can be simplified. Both of these can be divided by 3. So this would simplify to 1/4. Now here I would leave it as 1/4, but sometimes they will ask you to change it to a decimal. So in that case, you would just do 1 divided by 4, which would be 25 hundredths. And if they ask you to change it to a percentage, multiply that by 100 and you would have 25%. Again, it would clarify in the question whether they want a fraction, a decimal, or a percent. Okay, now let's look at experimental probability. A forest contains about 500 trees. You randomly pick 67 trees and find that 27 of them are oaks. What is the experimental probability that a tree in the forest is an oak? So first of all, number of times the event occurs. So what event are we looking at? Well, we're looking at how many times what did we find an oak tree. Well, we found that 27 times the trees were oaks. So that would be our numerator. Over how many total times was the experiment done? Well, you randomly chose 67 trees, so that's how many times the experiment was done. The 500 trees is just extra information that we don't need. Doesn't matter how many total trees are in the forest, it matters how many you looked at in your experiment. So 27 out of 67 cannot be simplified, so that would be our final answer. If they asked you to change it to a decimal, 27 divided by 67 is approximately 40 hundredths. And then if you multiply that by 100 to get the percent, it would be 40%. All depends what the question asks. All right. Now our next activity was what's in the bag, and that was dealing with independent events versus dependent events. So independent events are events that do not influence one another, while dependent events do influence each other. So let's take a look at an example of an independent event. It says, suppose you roll a red number cube and a blue number cube. What's the probability that you will roll a 3 on the red cube and an even number on the blue cube? First of all, let's talk about why this is independent. No matter what happens on the red cube, it has no effect on what happens on the blue cube. No matter what happens on the blue cube, it has no effect on what will happen on the red cube. So these are completely independent of each other. They can have no effect on the other one. So first let's look at the red cube. What's the probability that you'll roll a 3 on the red cube? Be careful here. You don't want to put 3 in your numerator. How many 3's appear on a number cube? 1. So that would be the numerator. Out of how many total sides on a number cube? That is 6. Now since we have 2 events, we're rolling a 3 on the red cube and an even number on the blue cube. That means I'm going to have 2 fractions, and remember what you do with those 2 fractions is you multiply them. So now let's calculate the probability of getting an even number on the blue cube. Well, even numbers on number cubes would be 2, 4, and 6. So there's 3 of them. out of how many total sides? 6. Now remember, you can simplify this and then multiply. You can multiply and then simplify. I prefer to simplify first. So both of these are divisible by 3. So really we're going to have 1/6 times 1/2, because 3 divided by 3 is 1, 6 divided by 3 is 2. So now when I multiply this, it would be 1/12. That's the probability that both events will happen, that you'll roll a 3 on the red cube and that you'll roll an even number on the blue cube at the same time. I roll both dice at the same time. 1 out of 12 chances that it's going to land on a 3 and it's going to land on an even number. Okay, now let's take a look at a dependent event. You have 3 $1 bills, 2 $5 bills, and a $20 bill in your pocket. What's the probability that you will choose a $5 bill, then a $20 bill, without replacing the first bill? Well, here's right away how you could tell that it's dependent. You are not replacing the first bill. Therefore, you will have one less bill in your pocket after you take out that first one. So we have to keep that in mind when we make the second fraction. So first, let's look at we have 2 events again, so let's look at the first fraction. What's the probability that you will choose a $5 bill? Well, how many $5 bills do we have? 2, so that's the numerator. Out of how many total bills? 3 plus 2 plus 1 would be 6. Now we want to multiply it by the next event. So now my next event is a $20 bill. So how many $20 bills in your pocket? 1. Now remember, you did not put that $5 bill back, so now there's actually 1 $5 bill left in your pocket. So 3 plus 1 plus 1 would be 5 now. You took 1 out, you did not put it back, so there's 1 less bill. Again, you can multiply and then simplify. I prefer to simplify, so let's simplify 2/6. Both of these are divisible by 2, so this would be 1/3. And then we're multiplying by 1/5. Multiply straight across, so 1 times 1 is 1. 3 times 5 is 15. So the probability that you have those bills in your pocket, the probability if you chose 15 times that you would choose a $5 bill and then a $20 bill without putting that first bill back would be 1 out of 15. All right, that's it for probability, guys. Bye-bye.